All right, welcome back to the almost normal physics Friday afternoon colloquium. So the first colloquium is traditionally one where the faculty present sort of a short overview of the research in an attempt to get students interested in working with them. And so that's what we're going to do here today. So our first speaker is Dr. Yongsheng Gao, who works on the Atlas experiment at the LHC and more recently at Icarus at Ringwald. Yongsheng, take it away.
Well, I'll give a short introduction to our experimental particle physics program, which sends students to CERN in Switzerland, and most recently to Fermi National Lab near Chicago. CERN stands for European Organization for Nuclear Research. In French, it is the world center for particle physics and the birthplace of several Nobel Prizes. The most important invention at CERN is probably the World Wide Web, and notice that's not Al Gore. So the $10 billion 70 miles Large Hadron Collider is located about 300 feet underground by the border of Switzerland and France. And the protons are accelerated to the speed of light and made smash head-on to create small big bangs, which bring us to the very beginning of the universe and allow us to study the fundamental building blocks of the universe. If we zoom in to this interaction point, you'll see the Atlas detector. So Atlas detector is the size of a 6-story building, and that's the size of a normal person. So it is designed to measure hundreds of particles coming out from per small Big Bang and measure them as precisely as possible so we can reconstruct the planets. The huge investments paid off. In 2012, Atlas and CMS experiments discovered the Higgs boson, which was responsible for the origin of mass. And this result was named by Science magazine as the 2012 Breakthrough of the Year, and resulted in the award of the 2013 Nobel Prize in Physics to the Higgs theory. So Fresno State joined Atlas in 2007 as the only CSU campus on Atlas or CMS. So the Higgs discovery was also the first research that CSU was ever involved in that has resulted in the Nobel Prize. Atlas collaboration consists of about 3,000 physicists from 38 countries all over the world, and among them, about 500 came from national labs and U.S. universities. So this includes 4 U.S. national labs: Oregon, Brookhaven, Lawrence Berkeley, and Stanford Linear Accelerator Center, together with many of the top research universities. So we joined in 2007, so to provide the outstanding Atlas opportunity to a wider CSU community, Fresno State Physics has been building up and leading the CSU Nuclear and Particle Physics Consortium with NUPAC. And NUPAC has grown to 11 campuses now. And every summer since 2008, I've been sending students from NUPAC campuses to work at CERN every summer since 2008, except last 2 summers due to COVID. And this summer, we have 9 students from 6 campuses work remotely on Atlas with our Atlas mentors at CERN. So far, over 100 students from 12 CSU NUPAC campuses have worked at CERN with our program so far. So this table shows the number of students and their campuses in recent years. And each year we had there were 6 students per year supported by NSF International Research Experience for Students, or IRIS grant, and each student received $5,500. So this list is the 12 students who worked at CERN in 2016, and their campuses they came from. The mentor, we work with mentors from Lawrence Berkeley, UC Irvine, Stanford, University of Chicago, and others, and their research projects. The students named in red are supported by NSF RES grant, including Olivia from Fresno State. So all those 5 students standing in the back to the right all came from Fresno State, plus Olivia, they all came from Fresno State. Olivia is now a PhD student at University of Colorado at Boulder. So the students, they have moved on to high-tech and also PhD programs at many of the UC campuses and also other universities, including institutions in Austria, France, and Germany. And the students also visited European cities before they returned to the US. So besides working at SORN, this summer, 2 Fresno State undergraduate students worked at Fermilab remotely for the first time. So our 2 students, Will and Gabby, they worked on analysis of the first eclipse data from the cosmic ray Tiger system, and they did an outstanding job. And each of them, they gave 3 talks at ICRA's Cosmic Ray Tiger Working Group. And my collaborator at Fermilab were very impressed, very happy, and she wanted them to return next summer to work at, continue to work at Fermilab with DOE support. And in the meantime, we are planning to send 2 more new undergraduate students to work at Fermilab with DOE support. The DOE support is $6,000 stipend plus the travel and housing allowance if working on site. So on November 11th, our after-semester students will give the department colloquium and talk about their research work. So if you're interested in working at SORN or Fermilab next summer, and what you need to do is to take my online class, Physics 163, which is open to all new tech campuses, and also join our experimental part of physics group. And then you can, and also you need to submit your application for working at SORN or Fermilab by December 15th. So you can join our group by shooting me an email. That's all I have. Thank you.
Here is Dr. Mihai Gherase. And Dr. Gherase is going to tell us about the medical physics program. So Mihai, take it away.
Hi guys, probably some of you know me. I run the medical physics program. Medical physics is an interdisciplinary part of physics. It actually is a big soup these days. It has everything from modeling diseases, treatments, imaging the human body. You can come from medical physics from different areas, computer science, mathematics, and of course physics. I mostly do X-rays, in particular X-ray fluorescence. Phenomenon discovered over a century ago, although only the past maybe 60, 70 years, the development in instrumentation, especially X-ray detectors and X-ray beams, have allowed us to expand the areas of applications, including medical physics. So it basically, briefly, you have an X-ray that observed via photoelectric effect. It excites the atom by taking an electron out. You have the vacancy, and the atom excites. And one of the processes is the X-ray or characteristic X-ray emission, or XRF. The other one is Auger electron. We can actually use both of these methods to do spectroscopy and figure out where this electron, where this transition was, and that way you can figure out what atom you're dealing with. As you see here, the curve here for electric absorption is much larger. You see this is the logarithmic scale here. It's much larger than all the other effects that go on, and that allows us to do that. This is my lab in Science 2 on the third floor. I have an XRF setup, so X-ray detector, a very small X-ray beam that can focus up to 20 micron or so, so very collimated. I also have dosimetry experiments. Sarah Coco was mostly the one working with this the past 2 years, and we work on different projects. Occasionally, I also work at the synchrotron, which are bigger X-ray facilities. They have very intense beams in pretty much all the electromagnetic spectrum, but mostly X-rays. This is some images of Lamborn. We're trying to do a more quantitative XRF analysis, actually measuring the concentration without the calibration. And that project is almost towards the end in terms of analysis and fabrication. And the last part I'm interested in, hopefully in the next year or the next few years, is to actually see if we can measure elements of interest to the human body, such as iron, copper, zinc, or selenium, directly in the human blood. So this would be an in vivo experiment where a very small beam would go straight into some superficial blood vessels, and with a signal and proper calibration, we will be able to actually measure the concentration. One of the motivations is that it's feasible. XRF can do that. It's critically relevant. Doctors always look at your iron level and other elements, specifically in particular. The COVID crisis kind of put some light on these metabolic elements. It's also non-invasive and will be 3 to 5 minutes, so it'll be practical and will be cost effective. Right now, all the analysis, pretty much all the elemental analysis, clinically or even for research, are done by this ICP-MS technology that was developed in the early 80s. It can go up to nanograms per gram, so it's very sensitive. However, the cost per measurement is, I think, a bit higher than what XRF would be, so something clinically relevant. These are some of the students I worked since I came here in some of the projects. If you have any questions, just reach out to me. I can tell you. Right now I'm kind of full, but I can maybe take in the future and take more students. It depends on the length of the project and what is needed.
Okay, thanks, Mihai. Next speaker is Dr. Fred Ringwald, and he's going to tell you about the astronomy program at Fresno State. Fred, take it away.
Yes, Fresno State Physics has a vigorous astronomy program with our campus observatory, our remote observatory, our projects with Hubble Space Telescope, other NASA spacecraft, and observatories worldwide. The students are welcome to participate in hands-on research on exoplanets, which are planets of other stars other than the Sun, cataclysmic variables, flare stars, starburst galaxies, quasars, and of course, black holes. Students now involved in research are Eric Gokin, who is writing a very nice thesis on accretion disk physics, Elisa Lee, who is putting together a very nice physics on accretion in quasars, the most energetic things known in the universe. They're typically 1,000 times brighter than the galaxies that they're in, that they are in. Chance Spencer, who is working on doing research on neutron stars, black holes, and novae, and Armando Guerrero, who studies star-planet magnetic interaction. Both Chance and Spencer planning to finish up their theses at the end of this year. Eric and Elisa plan to finish their MS theses at the end of the semester. And data sources we're currently using are observations from NASA's TESS spacecraft, observations from 3 automated telescopes in the Canada Real-Time Transit Survey, and Fresno State Station at Sierra Remote Observatories, to which Armando and I plan to go just after this talk, actually at 5, and we can stop there. Any questions?
Okay. Well, thanks, Fred. About the theoretical physics program. So the two characters in the that run the theoretical physics program. Actually, I should take it back. We actually have a new compadre who's sort of bridges theory and computation, and he's going to do a separate talk. Dr. Ettore Vitali.
He's also a character.
No, that's what I said. He is also a character. So, but Gerardo Munoz back there, and myself, Doug Singleton. We have a strong record of student publications and conference attendances. So why should you care about this? Well, if you're thinking of going to a PhD program, these are the things that set you apart. Okay, and like when you publish your first paper, when you publish a paper, you get a kick out. I mean, Gerardo. I mean, when you see it in print, it's like okay. Anyway, we provide a good background for PhD programs, but also for community college teaching. So at the pizza party today, many of you guys were like, I want to go into teaching at a community college. A lot of our recent graduates from our program are now community college teachers. In fact, I would say that's the most often career path most recently taken. Okay, and also industry. We have people working, former students working in industry that make way more money than these people. Okay, but the research areas we cover are classical and quantum field theory, gravitational physics, and cosmology, theoretical astrophysics. All right. Here's, for example, some of the stuff that we've done in classical and quantum field theory. This is actually mostly what Gerardo's done. So in 2009, he wrote a paper with this character, Dan Tennant, on some potential way to test string theory. Now, string theory is notoriously difficult to test. String theory is a theory of everything. It's supposed to explain like how everything in the universe works. Beautiful, except there's no test of it. So it's not, in that sense, it's not really science. So actually, Gerardo came up with some idea for potentially testing string theory, which was published here, and actually resulted in a Best Graduate Thesis Award for Dan Tennant, this very tall graduate student. Then Gerardo also worked with sort of this interface between classical general relativity and special relativity, where he was looking at sort of at the special relativistic Coulomb problem. So, you know the Coulomb problem that tells you how planets move around the sun in an inverse square law that orbits are ellipses and so forth and so on, yeah? So what if you throw special relativity into that? What happens? Well, this is what happens. You get orbits that look like that. Now, the co-author was a student, Ivana Pavic, who actually works at a community college out in Oklahoma. And this is a student of mine, Sylvester, and this is a research colleague, Mirab, who I haven't seen in a long time. But anyway, we were at a conference in Santa Barbara. So again, the point I want to make is we have lots of collaboration with students, with international collaborators, and we go to nice places to go to conferences. Not recently, though. More recently, Gerardo's worked on black hole physics, basically looking at how quantum effects affect the structure of black holes. And in particular, I think in this study, he was looking at charged black holes and how quantum effects change some of the pathologies that exist inside black holes. So inside black holes, you have things like horizons, you have singularities, and then inside the outer horizon, sometimes you have an inner horizon, and bad stuff can happen there. Bad stuff is like a non-technical term for various pathologies. And so the idea is quantum effects can basically ameliorate or soften these bad effects. And so that's what this study was about. And this is actually the student that Gerardo did it with, Jonathan Thompson. Jonathan finished his PhD at UC Merced and is now working for an industry company down in Santa Barbara area, yeah? Okay. So recently, this is work I've done. So I've worked with Michael Dunya and Tim Evans, which actually this is hot off the press. Basically, we worked on two things that probably don't exist, okay? But that's theory for you, all right? So we looked at the possibility of the existence of magnetic monopoles. What are magnetic monopoles? Do you know what a magnet is? It has a north pole and a south pole. Suppose you could cut that and you could make just an isolated north or isolated south pole, right? Then you'd have a monopole, a magnetic monopole. Now, the thing is, how do you make such a thing? We don't know. They're thought to exist in theories like string theory, but if you want to make something like this by cutting this in half, it doesn't work. You just get two smaller magnets, okay? Anyway, so we looked at the theory of magnetic charge with massive photons. Also, somewhat recently, I've been looking at phenomenological quantum gravity. So basically what happens if you include quantum mechanics and gravity in a single theory. And this work is basically these two papers. There's some other papers, but these are the most recent ones. And actually this last paper was with Michael Bishop, whom some of you may have had a class with. He's a math professor. And actually two graduate students, Jae-Young Lee, who's currently at William & Mary, and Joey Contreras, who's finishing up this year with his master's thesis. Okay? All right, so most of our projects are with graduate students. Gerardo, that's fair to say, right? The thing is, you need quantum mechanics, you need E&M, you need all this, and then by the time you get to the point where you can do research, you're graduating. Okay. However, I recently had some idea, which I call my YouTube project. So, how many of you had quantum mechanics? Okay. Oh, great. So 3, right? 4, right? So, you know what the spin of the electron is? The electron has an internal rotation. Can you think of that as any kind of spinning, as anything rotating?
Oh, Doug. So quantum mechanics is a little abstraction. It doesn't connect with physical reality very much.
No. Okay. I agree that that's what it seems like, and that's what a lot of the explanations are. But my point is, don't give up, right? There is actually a real reasonable explanation for things. And spin, this internal spin, basically, so according to Pauli, so if you said no, there's no physical picture of spin, you're in good company, okay? Because Wolfgang Pauli famously pontificated, spin is an essentially quantum mechanical property, a non-classically describable two values, okay? Wrong, okay? Now, why wrong? There's this nice article called What is Spin by Ohanian, where he actually shows that you can view the spin of the rotation of the electron as a rotation in the field, the Dirac field. So it is basically, with math, he just shows how going from the Dirac equation, you can calculate how the wave matter of the Dirac equation rotates around. And this is very similar to, how many of you guys have had optics? Oh, okay, right? So you know how electromagnetic radiation works. Like electric field, magnetic field oscillating like this, and you can have linear polarization where the light moves like this, and basically electric field oscillates up and down, magnetic field back and forth, and so forth. But there's such a thing as circular polarization, right? So as the wave propagates forward, it rotates. So if you do a calculation, right, of that circular polarization, what you find is it carries an internal angular momentum. You can do the same calculation with the Dirac field, and you get the same thing, except the internal angular momentum happens to be h bar over 2 rather than the h bar. So anyway, so this is nothing new. Okay, this is actually an old article from '86. But if you go on YouTube, if you go anywhere, if you go to textbooks, everyone goes, no, you can't understand spin as rotation. So what I want to do, I'm going to make a YouTube video of this.
But in the classical limit, spin does turn into angular momentum.
Yeah, that's exactly right. That's why there has to be some kind of picture for a rotation for spin. And Ohanian makes that point in the article. Anyway, so I'm getting carried away here. I'm just throwing a lot of buzzwords. But now the thing is, there's nothing new here. But what I want to do is make a pedagogical video for YouTube. Now, there's some difficulties, right? I don't know how to submit videos to YouTube. I don't know how to film.
It's easy.
I don't know. Okay. So anyway, what I'm looking for is, and I've talked with Dr. Vitali, and we've the for the visualizations, we've talked about stuff, and Tori, I promise I'm going to get back to you, and we'll at length talk about this more. But anyway, so if this is something that interests you, let me know, okay? Because like I have a lot of passion for this, but I lack the YouTube skills. Okay.
Doug, as a reminder, the department already has our own YouTube channel.
See, I didn't even know that.
Yeah, so I can post it for you.
Okay, anyway, so I harangued all the previous speakers to stick to time, and I think I've gone a little bit over my time, so anyway. So what can a student potentially expect from the theory program? Publish research in top-tier journals. Yes, we do that. Attend national and international conferences. By the way, I want to tell you, this year, the American Physical Society Far West Section meeting, unfortunately, is still going to be virtual, right? So it's unfortunate because you can't get to go anywhere, but it's fortunate because actually it's easy. You just log on Zoom, you have your talk, and that's it, right? Next year, however, the APS Far West Section meeting is going to be live, I hope, and it's going to be in Hawaii. Okay, so something to look forward to. Anyway, so we have a good track record of getting students to the PhD programs, the UCs, University of Wisconsin, University of British Columbia, UT Austin, and William & Mary, or into industry, AT&T Solutions, Bay Area startups, or community college JC jobs. And basically, this is our email. Like, we're both very accessible, open door policy. Come see us anytime. Okay, thanks a lot.
Doug, just one thing. Tell everyone the outstanding thesis.
Oh, yeah. Oh, and this talk, or this, hold on, that's the wrong way. Jay actually won outstanding graduate thesis for this year, which we actually only found out recently because apparently people can't do their work due to COVID. So.
Good job, Jay.
Alrighty, and the speaker is Dr. Ettore Vitali, and he's going to tell us about the brand new and very vibrant computational physics program. Ettore, take it away.
Okay, good evening, everyone. Thank you for coming. Most of you maybe know me. If you don't know me, pleasure to meet you, and I look forward to talking to you maybe anytime soon. So I'm here. Here's our pointer here. So as I mentioned, I'm the newest here. I joined faculty here in 2018, and I started developing our computational physics research group here. Since I came, I had the pleasure to work with a pretty long list of very talented students. We have Patrick here, and Joseph is here. So the very first member of the group, and probably the very last who just joined my group here. And then, as of now, we're having a very good track record in the sense that the 3 students who graduated and wanted to get into PhD places got admitted in even more than one, and now they are respectively at Boston College, Brown University, and UC Merced. And I also work with several collaboration groups. The most important are in New York, Simons Foundation, in Canada with my friend and postdoc researcher Peter Rosenberg, in Italy, where I am from, with my old university, and I'm recently doing some work with Sept and Queries, an independent researcher in the Bay Area. So, as you might have guessed, as of now, in the previous talks, you heard about 2 branches of physics that traditionally have just given shape to the field of physics. But in the last 50, 70 years, a new branch of physics is emerged and is pretty rapidly imposing itself as like the official 3rd branch of physics. And the whole idea is to see how a computer can help us do, understand, predict, and maybe solve physical problems. So broadly, it's a very interdisciplinary field, because if you want to enter the world of computational science, you need to have a pretty deep or to develop a pretty deep understanding of physical laws, because those are what we try to put on the computer and to understand them, you need to have a very solid understanding of math, because math is the language that we use to set up what the computer is going to do. And at the same time, the problems that we solve on the computer are most of the time mathematical problems. But also, you need to be able to talk to the computer, and that's what is typically called programming skills. And it's nothing but me trying to convince a computer whose mind is way different from mine, maybe better, maybe worse, who knows. But, and then, most recently, I'm seriously looking into the visualization field, and we can have a lot of intradepartmental and even outside collaboration. I'm applying for funding in that realm to see if I can get money, also to work on the pedagogical part of what we do. So most of my actual research is in the realm of quantum physics. And I often like to quote a very famous quote by Paul Dirac, one of the fathers of quantum mechanics, who used to say, and you may agree or disagree, that's not really the point of my presentation here, that really most of the physical laws, at least at the level of condensed matter and chemistry, are indeed known. The point is that we have equations, but we do not have solutions. And the main thing he was thinking about was the celebrated Schrödinger equation, which is the central point of quantum physics. And although it's true that you can write it in one piece of a small slide, but solving it is a different story. Who is in quantum? Who knows how hard it is to solve it beyond very simple application? And indeed, it's a very intriguing and rich equation, and underlying it, you may discover very fascinating phenomena like high temperature superconductivity. Even the inside of neutron star is known to be deeply and intrinsically quantum. And well, this is an artistic view. This is in reality water, but what I have in mind is vorticity in superfluids, and in particular vortices that are suspected to exist, basically are expected to exist in the depth of a neutron star. So what physics are we talking about? Well, whoever joins my group will be offered a long list of possibilities, including a lot of freedom and latitude to come with your own project. But if you are interested in physics, most of the physics I do is in the realm of cold atomic Fermi systems. Well, one of them is inside the neutron stars, but there are other cold atomic Fermi systems that can be engineered in the lab, or you can find cold atomic Fermi system in the depth of any material that surrounds us. And then unconventional superconductivity is one of my biggest topics, is where I have a maximum number of collaborations. Although as of now, almost 100% of the students who joined the group decided to enter the first chapter here. But I have a lot of room also for projects which are more mathematical and methodological, and in particular discussing algorithms and new ideas, techniques to solve a partial differential equation and similar, or projects that are connected to the physics, but that can be interesting on their own. And then another topic which is related to the design of computer experiments, all topics that sort of converge together in hopefully giving some robust description of those kind of phenomena. And then, as I mentioned before, most recently, visualization, and Doug and I can have long discussions about what we can do about this, and yeah, I'm very open to any other collaboration. So what working in my group would like? Well, my philosophy is mostly to teach by example. So I want you to be in charge of your research project. That can be very satisfactory and / or very painful depending on what you expect, because research is a painful part. I cannot lie to you. There is a lot of trial and error, a lot of experience, a lot of failure, and a lot of success. So normally you would be just part of a team, and it may be just you and me, or we can set up a larger collaboration. And you would build a plan, build your computer algorithms, running your code, getting your data, analyzing them, and possibly publishing and presenting them. As of now, from our group, we have more than 15 presentations at national and local events. We had one top-tier paper published, Patrick is an author on them, another paper was published a couple of years ago. We are having an internal review from American Journal of Physics, and we are hopefully waiting for a good answer, and we are ready to submit other papers. And then apart from the experience and the research, what I would like to give you as a benefit or like as a return from the commitment that you may want to invest in some project, well, you will certainly end up with very good programming skills, which is a kind of thing that looks very good on the CV and is particularly useful. And then, well, the typical science background, this is certainly not unique to me. This you will get from any group. You may work in data analysis skills, scientific communication, and then we will try our best to be your path toward the PhD and more. And second, I would like to be your advisor in the sense that I'm happy to discuss with you, share my experience, optimize your career possibilities. I never say no to that. I even advise students who are not in my group. And I'm happy to do students from my classes and so on. It's a very natural thing that I like to do. Also, just to mention, there are 3 classes that I developed since I joined. I maybe introduce more of them. As of now, my teaching load is already pretty full, but those are potential classes that may appear at some point soon. In particular, quantum information science. I have Patrick, who is a biophysics expert, who may help me in designing biophysics-related aspects. So that's it for me. Thank you for your attention, and I look forward to hearing from you.
Does anyone have any questions for Ettore? Don?
Boy, I got a question. That's a nice shirt you got there. Thank you. Anyway, on the 175T, are you getting students from the computer majors and things like that, animation majors, or only physics students?
No, I had also students from computer engineering.
Very good.
And yeah, I think I'm having computer scientists as well. Most of them are physicists, but I'm seeing students from other departments.
Do they have a major over there now called animation, you know? Animation.
Just a major.
Who knows?
An entire major.
That's what I was wondering.
I have no idea. Honestly,
I mean, it's be profitable, right? Probably.
Well, we do a lot of animation in my group. You see, in recruiting, I always do my animation.
So Don, I don't think the engineering department has something like that. That's sort of an interdisciplinary thing between art and engineering.
That's what it is.
And those departments,
Okay.
colleges don't intersect at all. Unfortunately, that's a.
Oh, sorry. So is open hearing to be offered every semester?
Most likely depend contingent upon enough enrollment. It used to be in the fall, but then we decided due to the graduate curriculum to make it in the spring. So yeah, I look forward to opening on a regular basis, 1 per year. Two times per year might probably be too much to have enrollment, and it wouldn't. But yeah, once per year it should be there.
Most graduate classes are only once a year, just because of the small number of students we have.
So as of now, the StatMac is supposed to happen on spring 2022. The 2 computer classes are one in the fall and one in the spring. They are expected to become part of the curriculum. The first one is the more introductory, where I do more programming, and mostly we play with simple differential equation from mechanics. We study harmonic oscillators, we go all the way to the Kepler's problem. We even try to do the 3-body problem if some student is motivated enough at the end of the class.
Yeah, with the computer, you can actually study chaotic systems too.
Yeah,
right?
we do.
So
It's a common thing we do. And it's something that immediately attracts a lot of enthusiasm in the class. But apparently students like, we cannot find the solution. Well,
Now, Ettore, how's this quantum computing coming to your field? I mean, what's that going to do?
the quantum computing, well, the hope is that the quantum computing can speed up the calculation that I can do now. So those are all called classical computers. Although it's a pretty wrong term because most of the computer works on quantum laws. If we hadn't quantum, we wouldn't have a computer.
Right.
Because all semiconductor physics, all those things are quantum. But the quantum bits, so the new, the breakthrough, may mean that we might become able to study very large systems with a complexity which basically means computer time, which would become way shorter. So we would be able to study, say, a system of 10,000 atoms in a few minutes, hopefully. I have friends working in the cutting edge aspects of that field. It's being very good.
Well, it still blows my mind. I mean,
It's very interesting,
I mean, just
and they do exist now, all the major companies. It is pretty far to scale really the algorithms up and to keep that information there. That is pretty hard. Also, as of now, that will be only random access memory. There is no way to say you have the storage in the computer.
Right,
you would lose everything.
Right.
If you save the file 2 days later, the entanglement would go down and you lose anything. But in terms of the gates, the operation, there is some good hope. All the biggest companies are investing.
They're investing in it, but yeah.
Okay, for another question here. So could you go back to slide projects?
The projects?
Yeah. So what do you mean in the when you say search for new probes for superconductivity?
New probe? Well, the problem is that actually, that's a very advanced question. Let me see if I can answer in a pretty compact way. So the problem is that we have some materials that are superconductors. We know that. But if you set up the theory of the same material using the laws that we are aware of, you would conclude that it is not a superconductor. So what's going on there? What's the missing ingredient? The problem is that when we face the equation of Schrödinger equation, it's very hard to theoretically detect conductivity, and in particular superconductivity. Most of the new generation superconductors, for example, are horrible conductors, which is very counterintuitive. The normal superconductors are very good conductors. You take from the periodic table, most of the metals over there, if you cool them down to very low temperature, they become superconductors. But sort of not so surprising, although it was 1 century ago. Because those are already very good conductors, you cool them down and you figure out. But in a modern one, they have all the properties that would induce you to expect that those are not superconductors. But indeed, you cool them down and you see the resistance drop from a pretty high value to 0. So how can we set up a theory and figure out if that theory is describing a superconductor or not? That is the kind of project my student Soban is gradually exploring that idea. Although with him we are now doing probes for conductivity. Probes for superconductivity will be the second level. It might surprise you because you might think that it's completely trivial. We take a multimeter, we connect and we figure out. But that's experiment. Theory, you have Schrödinger equation in front of you. So is that a conductor or not? I can assure you it's not an easy question.
Hasn't there already been a theory talking about like how superconductors integrate from the state of zero?
Say that again?
Hasn't there already been theory developed for superconductors?
Well, for normal, or it's called ordinary superconductivity, that we have a well-established theory written down in 1956 by 3 famous people named Bardeen, Cooper, and Schroeder. But for unconventional superconductivity, they were discovered nearly when I was born, and still we do not have a satisfactory theory. It's becoming a pretty angry community, and every year they get more angry, but it's still one of the biggest challenges. And there are connections also to quantum field theory, cosmology, There is no room for a lot of reflection.
So is the exotic superconducting community still angry?
Depends on exactly what they are up to. The cuprate community is pretty angry because we have this family of materials. We know everything about them. We know exactly their chemical composition. They have been measured on all possible angles, but still the theory is not complete. We don't have a theory that explains the critical temperature. We do not have a theory that explains many things in that way. And so they are gradually moving towards more exotic things. And that community is very active and engaged. But the cuprate community is still pretty angry. And we still hope to get somebody coming out with a good and satisfactory view. The big search in that realm nowadays is the room temperature.
Right.
Because that would have also a huge technological impact. Having current in the grids, minimizing the resistance and the joule effect or heat or dispersion.
Could that still be unconventional too? I mean, room
Well,
temperature
certainly very unconventional.
Yeah, I mean,
That's the less conventional.
Exactly, so that's the key.
Because the normal ones, you need to get to 4 Kelvin.
Right.
So minus 269, something like that. And so they may be very useful, but all the energy that you need to cool them down, that's already a huge expense.
Right.
The non-conventional now around 100 kelvins or so better. Liquid nitrogen versus superfluid helium versus liquid helium. And liquid nitrogen is way more available than liquid helium. Liquid helium is expensive and not so easily available. But still, also those materials are a bit toxic. They have a chemical composition, so they are not our thing. And graphene became one of the main characters of the investigation, and they're still actively looking. It's not really my field. But if I have a student that comes and wants to learn about graphene, that will be an interesting part. It has also relativistic quantum mechanics, because you get to the Arabic equation.
They're using that graphene for RO system for reverse osmosis filtration now.
Do they?
Yeah, graphene. I mean, that stuff's amazing stuff.
Yeah, graphene is perhaps the most versatile.
It really is.
Okay, so everybody? So no questions for anyone and like 50 questions for somebody. Okay, so I don't want to cut it Tori off, but let's let Don, and then there will still be time at the end for questions for all of us.
There you go.
Or you can ask Tori more questions. So,
Yeah, I bet you couldn't, man. You know Don's PowerPoint. I'm just going to come back here and speak without a mask till for enough weeks today, right? So real quick, all you students that are new students, right, that don't know me, I run the physics outreach program, all right? Now, there's kind of two big things that are run on campus and we do a lot of outreach. One of them is Steve and Kathleen's planetarium. That's a huge program. They do a museum and all kinds of stuff. And we work in connection with them too. And I have a class I actually teach. I see one of my students here right now. He's got his red shirt on. So you guys can talk to Tristan, right? He's a physics major, and he's just started the class the second week. You already had a class today, didn't you, bud? Taught your first, got up and taught his first lesson a day, and did a great job and having a lot of fun. So what this course is about, guys, even if you're not going to be a teacher in any field, this is going to help you get in front of people and talk. And if you got to get up and give a research talk, you need to get up and be able to talk fluently, right? Not stumble around, be confident. So this is going to help you, and no matter what you do, you're going to get up and be able to feel confident about getting up in front of people and talking to people. So that's one of the big things. But if you want to become a teacher, I'm going to teach you a lot of pedagogy. I'm going to teach you guys how to really teach by the seat of your pants. Because what you're going to find in all those education theories, they come up with a new one every year, right? Oh, you got to teach kids this way. I'm going to show you it's not that hard to do, okay? All you got to do is get them excited, motivated, and they take off, man. It's that simple. Because people love to learn things. They really do. People love to learn. We're just blowing it as teachers is what we're doing. We're doing a horrible job. And I've been out in the community, and I bet I've seen more schools than anybody I know of. I mean, I've been all over this valley, from little kids to big kids, and what we've got to get out there is good kindergarten teachers, guys, actually. You know, we always talked about high school physics teachers, and that is important. But, you know, we've been talking about that since the 50s, right? Oh, we need more kindergarten physics teachers. Because all of us in here that teach at a university, we know When you get kids from all over the world, you don't have your German and your Russian, your Japanese, your Chinese kids struggling with algebra. You know what I mean? But our American kids are, and we know it, right? They come into this school, they're not ready, they're not prepared, and it's our issue, right? We're not training these kids properly in good math and science skills, because you got to be a critical thinker no matter what you do, huh? That's what I always tell my students. I say, I don't care what you do in life, you need to understand when you look at that stupid Facebook, YouTube video, is that BS or real? You know what I mean? Because we know right now, it's out of control what these people believe, what they see on those things. And if you're a critical thinker, and you look at it from a good scientific viewpoint, you're probably going to come out with the right answer, all right? So if you want to take the course, guys, it's a 3-unit course, but I can turn it into a 4-unit course if you want to do a little research, too, all right? A little research in there, too. We can make that work out. And basically, it's a Thursday night course. We do a lecture for 2 hours, and that's where you learn how to talk, and you learn how to do your physics and teach it. And then we go out either Wednesdays or Fridays for 3 hours. And we go to schools all over the place. We have a blast. All right, that's it for me, guys. Unless you got any questions. Good. No questions? You guys have a great 3-day weekend.
All right, so that's the end of the colloquium. Our next colloquium is going to be actually not until September 24th. And actually it's going to be outside speaker Amy Furness, and she's actually going to tell us something also about the Veritas experiment and also about Calbridge. Okay, so you may have heard me talk about the Calbridge Scholarship. She'll also talk about that. So does anyone have any other questions for any of the speakers or for just Ettore?
Yeah, I have a question for Dr. Gao.
Okay.
Okay, so you had mentioned working in experimental particle physics from here. So what does that entail? Do we have like a collider here?
No. So there are only 2 possibilities. One is at CERN, which is near Switzerland. The other one is in Fresno, near Chicago. So what students do here is, so I offer online class every fall semester. And this is open. We built up a consortium with 90 campuses. So typically like 35 students from like 12 campuses will take my class. And then we submit the application by December 15th each year. And then by early January, like 12 students will be selected to prepare to work at CERN. So they'll take another online class, learn the skills and techniques. And then they'll be working at CERN during the summer. So they'll be traveling and working in Switzerland in the summer. And then this summer, now we have another program at Formula. So the students will do the same thing, take the online class. If they're selected, they'll take another online class to learn the Swiss skills. And then during summer, they'll be working at Formula.
Okay.
So no collider here.
Yeah.
But yeah, that's why everyone works at CERN. So they have like 10,000 people from all over.
So what do the students who are working do, which is prepare themselves for the summer?
That's right.
Okay. Okay, thanks.
Any other questions? No? Well, if not, have a good 3-day weekend. We still got plenty of snacks there, and see you on the 24th.